Bismillahirrahmanirrahim. This is ELE424 Analog Electronics 1, Video Pack 3, Video 7. We have completed AC model in the previous video, so now we are at AC fixed bias analysis and the voltage divider bias. My name is Wan Fazlida Hanim Abdullah. I'm from Faculty of Electrical Engineering, UiTM, Shah Alam, Malaysia. So topics covered in BJT AC small signal analysis. We had the same slide in our previous video, but now I've made point number 1, 2 and 3 green because we've covered those 3 topics. We are now going to look at fixed bias and voltage divider bias with bypass capacitor, and we will continue with these few following topics in our future videos. But for this video, we'll be only covering these 2 configurations. Okay, so the approach that we will be using is that we will demonstrate AC analysis on each amplifier configuration that I listed in the slide previous slide, by first finding the input impedance, output impedance and gain expressions. So what's going to happen is that for all these configurations, this is what we're going to do. From a given configuration, the AC equivalent circuit is drawn, assuming that DC analysis values are available. We already know how to do DC analysis from the previous video, so now we are going to do AC analysis. And when we do AC analysis, the DC supplies and capacitors will be replaced with a short circuit, and then BJT is going to be replaced with an RE model and redrawn. And the circuit is then redrawn for simpler analysis by removing or simplifying components due to the shorting out of DC supplies and capacitors in part 1. And the circuit is labeled with 2-port network parameters. Number 3 is that circuit analysis is carried out to get relevant parameter expressions. Okay, so all these 3 steps, I know this sounds still new for you, but I'm just listing it down because we're going to do all these 3 steps for all our configurations to do AC analysis, and we will explain this in greater detail later with examples. So this, being able to see the general approach like this will prepare you to do design and analysis of BJT single stage amplifiers for any of the configuration that requires the same approach. Okay, so we will now begin with the first configuration, common emitter fixed bias configuration. Again, in order for you to follow this slide, you should be able, you should have already done the previous video and do the relevant tutorials given to you by your course lecturers from the learning platforms. So this is the circuit. We have seen this, the fixed bias configuration, when we covered DC analysis. But now we're going to look at this same circuit, assuming that it's been biased at the required Q point in DC analysis. We're going to look at this circuit now, and we're going to do an AC analysis on this. Okay, so the fixed bias, as we know, has a resistance RB connected between the base terminal and VCC, and RC from the collector terminal to VCC. Okay, we've already also put down all the 2-port network parameters. Okay, we covered 2-port network in the previous slide when we did AC model. So if 2-port network sounds still vague to you, please have a look at that video for that revision page of 2-port network. So we have V in, positive terminal of V in connected to base terminal, and I in is the current that enters the positive terminal of V in, and Z in is the impedance that we look into the input port. Okay, and I out is the current through RC entering collector, and V out is positive at the collector terminal, and Z out is the impedance when you look back into the amplifier at the output port. So you may be wondering what port means. I got a message from one of the students to ask me what port means. Ports is just a pair of terminals that would allow communication between the circuit of interest and the outside world. So it's called a 2-port network because you have an input port, which is in this case at this point, at this node here, to the ground, and another is the output port, which is where you have indicated V out is with respect to ground. Okay, so before doing AC analysis, when we did RE model, we did mention that to find RE, the small RE, small letter R, small letter E, we need the DC value of emitter current IE from DC analysis. Okay, so also we know that we are going to short the circuits, the capacitors, the coupling capacitors, which we have covered in the previous slide as well. So we'll have to take note when we short those capacitors, what would happen and the effects of doing so to the components that is in the circuit. Okay. So now we know how the circuit looks like. We are now ready to redraw the AC equivalent circuit. Again, you should have already watched the video 6, because video 6 under the title of AC model not only covers RE model, but it also explains how to do an AC equivalent circuit and what to do next. So in this case, we will replace, as described in the previous lecture, we will replace DC supplies and capacitors with short circuits. Okay, and the DC supplies, that is VCC, then is connected to ground. When we did DC equivalent circuit, we did not do that. We maintained all the DC supplies because we were doing DC analysis. But in this case, we're doing AC analysis, so the DC supplies are shorted and it's connected to ground, which means I can now redraw and relocate for easier analysis. So RB is relocated instead of connected to VCC, because VCC is now become ground. I can redraw it and it can be seen in parallel with the input section. So will the RC be relocated, and it can be seen that RC is in parallel with the output part of the section. Okay. So now we're redrawing it. We're replacing the BJT with the RE model. Okay. We covered this last lecture as well. So BJT has an RE model which consists of beta RE, beta IB, and R out. Okay, RB and RC connected to ground is just as in the previous circuit that we had redrawn, and the two-port parameters, two-port network parameters, which is I in, Z in, and V in, and I out, V out, and Z out. The notation must tally with what we have identified earlier in the section. So I in still enters B, okay, but I out, which was earlier going from VCC through RC to collector terminal, now because we have relocated it, the direction now goes up instead of going down. Okay, and then having redrawn this RE model with the redrawn this AC equivalent circuit with the RE model, before we can proceed, we will need to determine beta here, RE, and R out, because beta, RE, and R out are values that we need to find. Okay? So beta comes obtained is typically obtained from a specification sheet or direct measurement using testing instruments that produce output characteristics, meaning it's either given, a value given in the data sheet, or you can take the transistor and measure it at curve tracer or semiconductor parametric analyzer that gives you output characteristics, and you can measure what beta is from there. RE comes from DC analysis, because RE comes from the diode AC resistance, which is approximated to be 26 millivolts per IE, and this IE, if you notice, this IE, this capital E here, indicates that it comes from DC analysis. Now this IB is small b, this IC is small c. Okay, because this IB and this IC are small signal currents in the small signal analysis. Okay, but this IE must come from the DC analysis. Okay. And R out here comes from either comes from specification sheet, or you can come from the measurement of output characteristics. We covered this in the earlier slides of early voltage, or you can calculate the gradient of the IC versus VCE curve where common emitter is concerned. Okay, now let's look at circuit analysis for two-port parameters. We're now at a specific circuit, still at the specific circuit of fixed bias. Okay, to find Zin, we'll have to find the equivalent resistance looking into the input port. So this is the input port, and we can see that RB is in parallel with beta RE. To find Z out, okay, the way to find Z out using two-port network is that we have to set V in to be equals to 0 because it's part of the procedure. So set V in equals to 0. When we set V in equals to 0, if we were to look at the redraw, I'm going to go back. Okay, if we set V in is equals to 0, it means that if I do Ohm's law here at beta RE, beta RE cannot be 0 because beta has a value, RE also has a value, which means IB, the small signal current IB, is going to be 0, which means this beta IB at the output section of this dependent current source is also going to be 0. Okay, and if that happens, it means that if I look back into the output port of to find Z out, I will find R out to be parallel with RC. Okay, so here I've already indicated as well that V in is set to 0, therefore small signal current IB is 0 amps. Okay, gain. This approach is applicable for most of the examples here. Okay, meaning that for almost all of the examples, I think, that we will be covering in this syllabus, will use this approach, where we will find V out with expression that has IB. So I can do V out here using Ohm's law because I know IB is going to flow through the parallel combination of R out and RC. Okay, I get that expression. Ohm's law, V out is equals to negative beta IB times R, which is RC parallel with R naught. So this is V equals to IR, but there is a negative sign here because this current enters the indication of V out. The terminal here is going to be negative, so that's why we have this negative sign here. If it had been V out were to be positive terminal here at the one below here, then you would have a positive sign here. But in this case, because the two-port network has already defined V out to be arranged this way, therefore this is going to be a negative value. And then we replace IB with V in. Okay, IB is equals to V in over beta RA. Again, this is Ohm's law as well, so there's nothing extraordinary here. This is Ohm's law, this is also Ohm's law. Okay, IB is equals to V in over beta RA. Now in this case, IB is positive because it enters V in through the positive terminal. Now what I want to do is that I want to replace the IB that I got from the output Ohm's law, output section Ohm's law, to become an expression that has V out and V in, because gain is V out over V in. So from this expression I can write AV is equals to V out over V in, and I can cancel off beta and I get RC parallel with R out divided by RE. Okay, now when one of the parallel resistances, if RC is parallel on R out, we've covered this as a revision in one of the earlier slides as well. When one of the parallel resistances are much larger than the other, the larger resistance is assumed as open circuit. And what do we mean by much larger? We say just 10 times, right? So if R out is going to be 10 times bigger than RC, okay, if R out is going to be 10 times bigger than RC, then we can just estimate that RC is not in parallel with any component, it's just going to be with open circuit, so we can ignore R out and it becomes AV is equals to minus RC over the collector resistance divided by the small signal model parameter RE. Okay, as well as if we use this concept, this one of parallel resistance are much larger than the other. We covered this in our previous slides. If you've forgotten about it, please have a look. Okay, so you have here, in fact, for the input impedance, I've also added this term here. If RB is going to be 10 times bigger than beta RE, then you can actually ignore RB. Okay, assume that it's open circuit and that Zin is equal to beta RE, approximated to beta RE. So Z out is also the same thing. If R out is going to be much bigger than RC, okay, if R out is going to be much bigger than RC, therefore our output impedance Z0 is going to be RC. Okay, and we do expect that because R out is typically a large value. Okay. Okay, so now also maintaining the information about gain, we got this from the previous slide. Okay, I just copy paste here. Based on the derived expressions, now we're looking at this expression of gain and going to have some insight to the expressions. AV here is independent of the term beta. Okay, even though beta was used to determine the Q point and RE, but when you get AV, it's independent of beta, and that's good, right? Because now you can determine AV. Okay, if you can make RC small, small enough compared to R out, you can fix AV by fixing RC and fixing the Q point to get the IE that you want without it being depending on beta in its direct expression. Okay, but we do use beta to get the Q point and IE. Okay, so expression of AV. Okay, still having some insights from this expressions of the voltage gain. The expression of AV, we can also see that there is a negative value here. Okay, we know that earlier when we found V out, it had to be negative because using Ohm's law, the current was entering V out through its negative terminal. Okay, but what does it mean to have AV negative? It means that there is a 180 degrees phase shift that occurs between the input and output signals. When the input is in its positive cycle reaching maximum peak, the output is in the negative cycle reaching the minimum peak. And you can actually simulate this. We'll be having, I hope there's time for simulation videos in coming weeks. Okay, where we have the input going from maximum to minimum, and you will expect that the output will go from minimum to maximum and minimum to maximum with that 180 degrees shift. Okay, we are now ready for an example. So we have here a fixed bias circuit here. Okay, and then we're asked to find RE and then find Zin, calculate Z out, determine AV. Okay, and repeat part C to include R out to be 50 kilo ohms because BCD states that R out should just be assumed to be large enough as an open circuit. Okay, so this is a fixed bias circuit and we need to do all this. Now if I look at this, I know that part A, I need to do DC analysis, not AC, to find RE. Okay, because I need the value, the current value, IE. So once I find RE, then I go into AC analysis to answer the questions BCD. And I have also included this. This is small as usual. I've just put this together in one piece of paper to show you so that you can have a feel of how the solution when written on paper is going to be like. So it's not going to be that difficult even with the DC. Okay, this first part is for DC analysis, and when I do DC analysis, I know what I want is just IE. Okay, so I do DC analysis, then I do AC analysis required to AC equivalent circuit with the RE model. We're going to need to redraw the circuit and then find expressions of Z out and Z in using equivalent resistance, and then find expressions for AV using Ohm's law, and then for the question it just wants to do some investigation and R out. Okay, so now let's have a look at the solutions that we have previously here. Okay, so I'm gonna do it bigger so that we can see how it looks like. So when I do DC analysis, okay, I know I do DC analysis because I want to find IE. I want to find IE because I want to use RE in the AC equivalent circuit RE model. So to find IE, I need to consider the input loop. And when I do the input loop, I just need to do a KVL. I know that VBE is going to be 0.7 volts as an estimate for a silicon PN junction between base and emitter. So when I do KVL, I get negative 12 plus IB times 470 kilo ohms plus VBE, which is 0.7, equals to 0. Okay, and that gives me IB equals to 24.04 microamps. And then KCL. Okay, I do KCL here, or you may already be familiar now because you are familiar with the IE is equals to IC plus IB, which becomes IE is equals to beta plus 1 IB. It's the same thing here. Okay, and I get here IE because I already know that beta is 100 and I know that IB is 24.04 microamps. I find that IE is 2.428 milliamps. And if I want to pass this to the AC analysis, it will go into finding the RE model parameter, where RE is 26 millivolts over IE. Okay, this part we have not done in DC analysis. This is entering AC analysis. So before we enter AC analysis, this is the value that we need to find. So it's going to be 26 millivolt divided by 2.428 milliamps, and that is equals to 10.71 ohms. The thing that maybe we'd like to take note here is that the value of RE is small, 10.71. But when we put this value RE in the RE model, it becomes beta RE. So beta is a large value, so you can expect that beta RE is going to be a larger value than this. So now we are ready for AC analysis. When we do AC analysis, we know that the capacitors are short circuit and the DC supplies are also replaced with short circuits, and it goes down directly to ground, therefore. So now RB can be relocated and drawn aligned with the input section, because both are connected to grounds, and we can see here that RB is parallel to the input section of the base emitter terminal and Vin, and RC is parallel with Vout output port. Okay, so we are given that RB is 470 kilo ohms, RC is 3 kilo ohms, beta is given to be 100, and Rout is estimated to be an open circuit as asked in the question, as directed in the question. And we found that RE is 10.71, therefore beta RE is going to be 1.07 kilo ohms. Okay, so when we write this model, these values beta RE and Rout can all be values, but this expression beta IB, this IB here is a small signal model parameter, small signal current. IB is left at IB. So now we're ready to consider the network parameters. We'll first look at Zin and Zout, which is the input and output impedance. Now I've grayed out the AC equivalent circuit here, which has the RE model in, because I'm not redrawing it again. This is just to indicate that I'm just this is just being copied and pasted here, so that because it's easier for us to refer to this, because otherwise if I were to fit in everything in the same slide, in the same screen, the font would be too small for us to see. Okay, so I'm just copying from the previous screen so that we can refer to it easier. So Zin is going to be the parallel combination of RB and beta RE, which will give me 470 kilo ohms parallel with 1.07 kilo ohms, and the value is equal to 1.07 kilo ohms. Now maybe there's going to be a slight difference here if you consider the more significant figures here, but what it's saying is that yes, 470 is more than 10 times 1.07, so you do expect it to be almost equal to beta RE. Okay, Zout, in this case, for us to set to find Zout, we need to set Vin equals to 0, and if Vin is set to be equals to 0, that means that IB is going to be equal to 0, because this is Ohm's law, parallel, Vin is equals to IB beta RE. And beta RE is not 0, because we know beta is not 0, RE is also not 0, so it has to be IB that is 0. So the dependent current source here is generating equals to be 0 amps. So what Zout sees is only RC, because Rout we have been instructed to treat it as an open circuit to be equal to approaching infinity. So Zout is 3 kilo ohms. When I want to calculate voltage gain, okay, we covered this. I mentioned this in the previous few slides. We first find Vout using Ohm's law, and our Vout, okay, this time Z out is, we don't set V in equals to 0 anymore because we have already calculated Z out. Setting V in equals to 0 is only for calculating Z out. Now to find a voltage gain, we'll have to find an expression. This Ohm's law is going to be V out is going to be equals to minus beta IB RC. Minus beta IB is going to be this current, which will enter RC because R out is an open circuit, so it's not included here. It enters RC and it's negative because it enters the negative terminal of V out using Ohm's law. Okay, and we have this expression of V out which has the term IB. Now we look at the input part. At the input we have a V in is equals to IB times beta RE. Okay, also from Ohm's law. And what I'm going to do is that I'm going to have, what I want is an expression that has V out and V in together in the same equation. I'd like to replace IB in V out here. So I have this expression and I find that beta is cancelled. So I have AV is equals to V out over V in, which is the way to find voltage gain, is going to be equal to negative RC, which is the collector resistance, divided by the small signal model parameter RE. And this is going to be 3 kilo ohm divided by RE, which is 10.71, not beta RE anymore, but RE, 10.71, and the value is going to be negative 280.11. And we know that this negative means that V out and V in will be 180 degrees shift out of phase. Okay, so the last part of the question says, now what if R out is 50 kilo ohms? Not infinity, not an open circuit. Now if R out is 50 kilo ohms, Z out is going to be RC parallel with R out. Okay, so if I were to just go look at the previous slide so that I can have a look at the image, Z out is going to be RC parallel with R out, and therefore I need to use the parallel resistance formula to find the equivalent resistance. I'm going to find this to be 2.83, which means if I compare it, if I were to treat it with an infinity instead of 50 kilo ohm, there will be about 5% difference, 5 to 6% difference. And for the voltage gain, okay, the same process. I need to find an expression for AV, but now when I find V out, it's the current from the dependent current source beta IB. It does not enter just RC, but the parallel combination of RC and R out. Okay, V in is still the same. I put it in here, so the value that I find RC parallel with R out as the value that we found earlier is 2.83 kilo ohms divided by 10.71, which is the value of small signal model parameter RE, and I get this to be 264.24 compared to what it was if R out were to be infinity. AV would be negative 280. Okay, which means again there is about 5 to 6% reduction there. If R out becomes smaller, gain will also become smaller, which goes on to me commenting in my solution that with lower output resistance, output impedance is lower and voltage gain is reduced. So for us to have an ideal situation, R out should be as large as possible so that the output impedance is as big as possible and that the voltage gain is not reduced. Okay, now we are ready to go on to the common emitter voltage divider bias configuration with a bypass capacitor. And what is the bypass capacitor that I'm talking about? Okay, this is the voltage divider bias circuit, nothing new, we've done this in the previous slides. Okay, but now we have a bypass capacitor CE here, which is in parallel with RE. Okay, right, now before we go on, we know that we have to do DC analysis before we go into AC analysis, because we cannot solve a circuit of an AC amplifier without setting it into the Q point. So either the question itself, the situation itself, or has already calculated it for you and gives you the DC parameters, or you will have to do DC analysis. And if we want to do DC analysis with voltage divider bias, if you recall when we did DC biasing circuit in the first, I don't know, 3 videos, 3 or 4 videos, we see that if it's voltage divider bias, we have 2 methods of solving this. Either we use exact method using Thevenin equivalent circuit, or we can use approximate method. With approximate method, beta RE there is a condition which is beta RE greater than 10 R2. Beta RE here times beta must be greater than 10 times R2. If that is fulfilled, then we can use voltage divider rule for finding VB here, because we assume that all the current from VCC of R1 goes down all the way to R2 through ground, because if beta RE, which is the input impedance, if you see it just from between this base terminal reflected back by the feedback action of emitter resistance, then if beta RE is so much bigger than R2, then what you're saying is that it's not going to draw significant amount of current. In fact, compared to the current that goes to R2, you can actually say that it will not draw any current. So all the current will go through R2, which means if that happens, you're saying that R1 is parallel with R2, and if R1 is parallel with I2, you can use voltage divider rule to calculate the voltage at this V bias. So I'm just repeating myself. I'm going very fast here because this has been covered in the DC analysis section. I'm just repeating it here because we're going to use it later in the next slides when we do examples. Okay, also take note parameters of two port network parameters: I in, V in, Z in, I out, V out, and Z out. Okay, so before doing AC analysis, the parameter IE is needed, this parameter IE, and we should also take note of the components that will be shorted and the effects of doing so. Particularly in our situation here, because there is a capacitance here, it will be shorted out, and RE will not appear in our AC analysis, okay, because it has been shorted out. And just in case you're wondering, we mentioned this in the previous lecture. So why is it that we have a bypass capacitor? Well, sometimes we want to increase the gain, fluctuations, and we want the DC to go down all the way to the ground through RE, but the AC fluctuations would be separated to the path CE. Okay, anyway, there is a reason for the bypass capacitor. So let's draw the AC equivalent circuit. Okay, it's just like the fixed bias, except that RB is replaced with R prime, which is going to be R1 parallel with R2, because the DC supply connected to R1 is replaced with a short circuit connected to ground, so which means R1 and R2 is not now going to be in parallel. Okay, so this is what I meant here. So R prime is going to be R1 parallel with R2, and we have relocated for easier analysis. R1 is parallel with R2, is relocated and can be seen to be parallel with the input section, and RC is parallel with the output section. Now we need to determine beta, RE, and R out, because we need this as values if we want to find the output parameters in the two-port network parameters in terms of values. So the circuit is similar to the common emitter fixed bias configuration, AC equivalent circuit, because of the bypass capacitor. So even though it's a voltage divider bias and there is an RE, but because of the bypass capacitor, the emitter resistance here is not seen, and R1 and R2 can be found as the equivalent resistance of its parallel combination of R1 and R2. So now we are ready to find Zin. So if we look into the input port, Zin is going to be R1 parallel with R2 parallel with beta RE, okay, which is the input, which is the RE model parameter, and then Z out is just going to be RC parallel with R out. Gain again is the same thing, nothing new. We find V out, because V out is going to be Ohm's law of beta IB going to RC parallel with R out, and this negative sign because it enters the negative terminal, and IB is the same thing really with the fixed bias. So IB is V in divided by beta RE, and the expression for AV is given that way. And so again, if the parallel resistance are much larger than the other, the larger resistance is assumed as open circuit. So in this case, AV is assumed to be just RC, negative RC divided by RE, because if R out is 10 times bigger than RC, and Z out 2 is going to be, we do expect that R out is going to be bigger than 10 times RC. But in the case of a voltage divider bias, maybe this won't happen so much because, well, we'll see later, because now R1 and R2, which is equals to R prime, the equivalent value, is not as big as RB. Okay, and also again it is negative, so the negative is because of the it indicates that there is a 180 degrees shift between V in and V out. Okay, example. Same words, okay, meaning that we find RE and then find Z in, Z out AV with R out estimated as open circuit, and then repeat parts C and D to include R out equals to 50 kilo ohms, and compare the results. Okay, except that our circuit now is a voltage divider bias configuration. Okay, again, everything is just too small here, but because I have put it purposely here, I will treat it in a bigger font later, but just so that you see what is involved if you're doing it on paper. So the first part here is for me to do DC to get the value IE so that I can find RE, and then I put the RE model, okay, draw the AC equivalent circuit, and then we do calculation of Z in, Z out and AV, all using mostly Ohm's law and equivalent resistances technique. And then we investigate the effect of R out if R out is 50 kilo ohms instead of infinity. Okay, so okay, this is the first part of the DC analysis. Now first I want to check, because I want to find IE, but for me to find IE I need to know whether I should do it using Thevenin equivalent circuit or I should be using approximate method. So to check whether it fulfills approximate method, I need to check against the eligibility criteria, beta RE greater than 10 R2. Okay, so beta RE I find to be 135 kilo ohms, because beta is 90 and RE is given, also given, both of these are given values, 1.5 kilo ohms. So it's 135 kilo ohms, and 10 R2 is 10 times 8.2 kilo ohms, which is 82 kilo ohms. So yes, beta RE is greater than 10 R2. It is fulfilled. Therefore, I do not have to find the Thevenin equivalent circuit. I can choose to want to use voltage divider rule. So voltage divider rule, which means that I want to find VB. Okay. So it's VB is equals to 8.2 kilo ohms divided by 8.2 plus 56 kilo ohms across the what is the voltage drop should be 22 volts. So I get VB to be 2.81 volts. Now from there we know that VBE is 0.7 volts, right? So if VBE is 0.7 volts, that means that VB minus VE is equals to 0.7, and I can rearrange VE to be equals to VB minus 0.7, which is 2.81 minus 0.7, and I get VE equals to 2.11 volts. Why do I want to find VE? Because I want to find IE, so that I can find RE. Okay, so from VE I can find IE using Ohm's law, which is equals to 2.11 divided by 1.5 kilo ohms, so I get 1.41 milliamp, and RE therefore is 2.6 millivolts divided by 1.41 milliamps for IE, and I get it to be 18.44 ohms. Just another comparatively small value, just like in the fixed bias. Okay, 18.44 ohms, and I will carry this into going into AC analysis. So when I do AC analysis, okay, this is the AC equivalent circuit. I can find R1 here. I can find R prime, I wanted to say. R prime here from the parallel resistance of R1 and R2, because R1 is given to be 56 kilo ohms and R2 is given to be 8.2 kilo ohms, giving me an equivalent resistance of 7.15 kilo ohms. Okay, RC is also given to be 6.8 kilo ohms, whereas R out we are instructed to assume that it is open circuit. Therefore the value is infinity, and beta is given to be 90 in our question here. Okay, so we have already found RE, which is equals to 18.44 ohms when we did DC analysis. So beta RE is going to be 90, which is the given beta, times RE, which is the value that we found for RE, 18.44, which is going to be equals to 1.66 kilo ohms. Now we are ready to go on to the next slide, which is calculating the two-port network parameters. Okay, so let's calculate the input impedance and the output impedance. So the input impedance, again, I have copied the image of the AC equivalent circuit here. I'm not redrawing it, I'm just trying to fit in all in the same slide here. So this is just referring to what we've drawn in the previous screen. Okay, so Zin is equal to R prime parallel with beta Re, giving me 1.35 kilo ohm, where R prime has been found to be 7.15 kilo ohm and 1.66 kilo ohm is the value for beta Re. Okay, and Z out, to find Z out, as we know, the procedure for two-port network says set Vin equals to 0. When Vin equals to 0, IB is going to be equals to 0 because beta Re cannot be equals to 0. So that when we do Ohm's law across here, because Vin and beta Re are parallel, so beta Re is not 0, so it's IB that has to be 0. Okay, so if IB is 0, this dependent current source on the output side here is also going to be 0, and since R out, we have been directed to treat this as an open circuit, all that Z out sees is RC, and RC is 6.8 kilo ohms. Okay, so for voltage gain, again, we just want to find an expression of V out over V in. So how do we do that? Just the same as we did with fixed bias, we treat Ohm's law at the output part, and Ohm's law is V out equals to beta IB, which is the current here. Okay, because now we are not calculating Z out anymore. So now IB is not 0 anymore. Okay, IB is a value that we indicate as the small signal current, I with a small letter B. So beta IB is going to enter, if there is an R out, it would be RC parallel with R out, but because we have been instructed to assume R out to be open circuit, so beta IB will all go through RC. Okay, and Ohm's law at the input part will just be IB times beta Re. So I can replace IB here so that I have an expression of V out and V in only, so that I can write V out over V in, and it's going to be equals to negative RC over small signal model parameter Re, which is going to be negative 368.76. And doing the last part of the question, if R out is equals to 50 kilo ohms, okay, Z out will now have to consider 50 kilo ohms, which is going to be 5.98 kilo ohms as an equivalent resistance of RC and R out. And then if I compare, if I in the beginning part, in the earlier part, sorry, we did R out approximated to be equals to infinity, but if Z out, if R out is 50 kilo ohm, Z out here is 6.8 kilo ohms, and that's 12% difference compared to our earlier example, which we had an for fixed bias, which was 6% difference. Okay, the same thing as gain. Okay, if R out is infinity, we would have gotten negative 368.76, but if R out is 50 kilo ohms, we would have gotten 324.3, which is a 12% reduction. So the difference here is more significant, okay, for part E than compared to part C and D, because the condition of R out, which is 50 kilo ohm in this case, is not going to be bigger than 10 RC. R out is going to be 50 kilo ohms, which is the value that have been given, and 10 RC, because our RC now is 6.8 kilo ohms. In the fixed bias example just now, which had a 6% difference, it was 3 kilo ohms. So this condition was fulfilled, but with 50 kilo ohms, this has not been fulfilled, and we do expect that the difference is more significant. So we're at the end of this video. This is the end of the fixed bias and voltage divider bias configuration. We will take the same approach for the next subtopic of emitter follower and common base configuration, and we'll finish off the BJT AC analysis with that video. So see you in the next video. Bye bye. Assalamualaikum.